In this video, we're going to talk about Euclidean space, which is a concrete example of a vector space, which we're going to talk about more abstractly when we get into Chapter 5. But I wanted to start with this particular vector space because you should be very familiar with it already. So by Euclidean space, we mean the set of all ordered n tuples, so x1 out to xn. Each of the components of this tuple has to be a real number. And we denote Euclidean space by Rn. Now, you're probably already familiar with a couple of these. When we talk about R2, that would just be the set of all ordered pairs, so your usual xy plane, vectors in the xy plane. Or if you had ordered triples, that would be vectors in space, in your xyz space, in Euclidean space. So geometrically, when we talk about vectors, we typically think of having a starting point, having an ending point. We put them in what's referred to typically, I think, as standard position. So we have the initial point of the vector starting at the origin, and then the end point of the vector ends at what the point that's represented by the tuple as well. So give you a specific example here. If we're in R2, if we talk about the vector 2, 4, we would have the point 2, 4, and the vector would go from the origin and point out to the point 2, 4. All right, so I wanted to give you a concrete example because, again, you should have already been familiar with these kind of concepts before this class. But the reason why I want to give you a concrete example is because later on we're going to abstract these notions and it won't be nearly as concrete. So you wanted to have something to fall back on to remember what we're really talking about when we're talking about vectors. So in general, when we talk about a vector space, and specifically right now we're talking about Rn, we define two operations on our vectors. One of them is addition, taking two vectors and adding them together. The other is scalar multiplication, which means we take a vector and multiply by a number. So in Rn, we already know how to do these operations. We've talked a little bit about them when we did determinants and motivated the determinant. We talked about it geometrically. We're going to approach it more algebraically because this is an algebra class after all. So let's say we had two n tuples in Rn. Then when we talk about adding these two things together, the x and the y, then we would just add component-wise. So when we take the vector x plus the vector y, we'll just get this as our result. If we do a scalar times a vector, well, we'll do this just like we've done it before. We'll take the scalar and multiply it by each component. Just a quick note about notation. Notice that when we talk about vectors, we use a bold-faced letter when we're printing it. If it's in the book or on the screen that I have here. But if in general when we write it, we'll write a little arrow over the top of it to represent vector, and we've already seen that notation in class. Another idea that we need for vector spaces is the idea of the zero vector, the additive identity, if you will. So for the Euclidean space, this is a pretty simple concept. If I want the additive identity, if I want to know what vector do I add to an arbitrary vector and get that vector back again, I would need to add zeros in every component. That's just by the way that the addition is defined. Another concept that we'll need is the idea of additive inverse. What gets us back to the additive identity? What gets us back to the zero vector? We do note that as usual with a negative x, like we would any other additive inverse. And for vectors in Rn, the additive inverse is just obtained by taking the negative of each component in the vector. So when we start talking about abstract vector spaces, there's going to be a bunch of axioms that have to be satisfied in order to be an abstract vector space. And we'll talk about more about that when we get to it. But I wanted to give you a little taste of what I mean by these axioms and how to go about verifying that the axioms are actually met by a particular way we say we're adding or multiplying. So if we have vectors in Rn, so we've got x, y, and z are representing vectors in Rn. C and D are just representing regular old real numbers. Those are our scalars. So we've got three vectors and two scalars here. Then the first property we have is that vector addition is commutative. The order doesn't matter when we add. The second property here that we have is that vector addition is associative. We can regroup however we want. The third property talks about that idea of additive identity that I just mentioned on the last slide. When I add the zero vector to anything, I get that thing back again. The fourth one has to do with the additive inverse. The whole idea behind that, of course, is if I add a vector to its additive inverse, I get to the additive identity. It's the whole point of an additive inverse. The next ones have to do with scalars. So these are actually a little bit more interesting because notice what the operations are. Here it says I do a scalar times a vector and then do a scalar times that vector. It's the same thing as multiplying the two scalars together first and then multiplying it by the vector. This is kind of an associativity idea, but notice that the operations are taking place. This is really a vector operation. This is a scalar operation. So the operations really are different, but they have to behave nicely with each other. We also get scalar product distributes over vector addition. Then we also get that scalar product distributes over real number addition. Notice this is adding two real numbers together. This is adding two vectors together. So again, that idea of the notion of the operations are taking place in different spots with respect to different types of objects. And then the last one says that if I take the scalar 1 and multiply by x, I just get x back again. Pardon me. All right, so let's go through a proof of one of these properties. I'm going to do a proof of f here. Property f, this distribution property. So we're going to go through and show how using the definition of the vector addition here, we can get, and the scalar multiplication, that we can get this property. All right, so I just substituted in the components for x and y. These are adding these two vectors together first. We add component-wise. Then we know that our scalar multiplication is defined by taking the scalar times each individual component. These are now real number multiplications here. This is not real number multiplication here. This is vector, scalar vector multiplication, right? Scalar times a vector. So this has to do with a vector operation. But now that we've actually done that, we have real number multiplication, so I can distribute normally. Cx1 plus Cy1, and so on down the line. We recognize this as the sum of two vectors, Cx1, Cx2 out to Cxn, plus Cy1, Cy2 out to Cyn. And recognize that this is the scalar c times the vector, and the scalar c times this vector, which is just cx plus cy. So we've verified property f. So when we're doing this for abstract vector spaces and different notions of addition and scalar multiplication, we're going to have to verify axioms like these. So what I would suggest is see if you can practice some of these other ones and make sure you can prove those particular properties. Because again, the idea of being able to prove these things is going to pop up later when we talk more about stuff in Chapter 5.